Pop quiz. Suppose we write in Lean a function named makeInfiniteList that calls itself on exactly the same argument with which it was called. Unsurprisingly, the type checker rejects it with the message, failed to show termination. Suppose, however, that we suppress the error. We say, here's a fake proof of termination. Sorry. Now the function does type check successfully with a warning. And my question to you is, what happens when we apply it and try reducing it? Does it fail? If so, with what error? Or do we get a value? If so, what value? Or does the reduction continue running forever? I want you to think about this question in the background. Meanwhile, let's modify our function so that it divides its argument by 2 before making the recursive call. Now it's actually possible to provide a real proof of termination. Yes, n plus 1 divided by 2 is less than n plus 1. So we should rename the function, perhaps as makeFiniteList. The behavior of this innocent-looking terminating function is the main thing I want to talk about today. 2.5 years ago, on Lean version 4.4, makeFiniteList would explode in your face. Called on a reasonably sized argument, such as 1024, it would trigger an error, maximum recursion depth has been reached. Which is ridiculous, right? It only needs to call itself like 10 times to do this computation. And if we increase the allowed recursion depth, then we get a different error, maximum number of heartbeats has been reached. What is going on? Back in 2023, I made a video documenting my attempts to better understand this behavior. The main thing I learned is that functions like makeFiniteList use what I've taken to calling fancy recursion, that is, recursion over a well-founded relation. Unlike in simpler structurally recursive functions, such as factorial, where the argument to the recursive call is a subterm of the input argument and termination is intrinsic, with makeFiniteList, the recursive argument is the result of an arithmetic operation, and therefore necessitates an extrinsic proof of termination. Lean's elaborator, whose job is to translate user-facing source code syntax into the lower-level kernel language, combines the termination proof and the function body using a fixed-point operator named wellfounded.fix. And although wellfounded.fix is quite elegant in its generality, it brings a steep cost in terms of efficiency. In Lean 4.4, the number of steps required to reduce makeFiniteList n is on the order of n squared. The makeInfiniteList function also uses this same kind of fancy recursion, though with an invalid termination proof, and at this point we can give an outdated answer to our initial pop quiz. As of Lean 4.4, reducing makeInfiniteList 5 returns a value. In particular, it returns a list where the first element is 5, and the remainder is a complicated term involving acc.rec, which you might recognize from the implementation of wellfounded.fix. When we turn on display of proofs, the term gets quite a bit more complicated, and definitely no longer fits on a single screen. We can see that our fake termination proof has propagated into many instances of the sorry axiom. These are what block further reduction. To summarize, the reduction successfully completes a single iteration of makeInfiniteList, and then, while making the first recursive call, it gets stuck inside some large, complicated proof normalization. Anyways, that's what fancy recursion looked like in Lean version 4.4. In later versions, things have changed. Lean version 4.7 added a new tactic called Omega, which can automatically prove facts about linear arithmetic. In particular, it can handle the termination proof of makeFiniteList. Furthermore, we don't even need to explicitly invoke it, because Lean 4.7 includes Omega in the default termination tactic. Sweet. A few months later, Lean version 4.9 eliminated most occurrences of the recursion depth error, albeit via a rather blunt mechanism. Now any definition that uses fancy recursion gets automatically marked as irreducible. That is, Lean dodges the problematic reduction by declining to even try to do it in most situations. We can always restore the old behavior on a specific definition by adding a semi-reducible attribute. The most important change that I want to talk about, however, landed more recently with the release of Lean version 4.27. To set the stage for it, consider how we might try to avoid the use of fancy recursion in makeFiniteList. If you watched my previous video, you may remember a workaround for this kind of situation. We can split out a helper function and make it structurally recursive on a new parameter, perhaps with the evocative name fuel. Assuming that we provide it with enough fuel, this helper function gives us exactly the same answer as the original function. But how much is enough? The fuel decreases by exactly 1 on each iteration, while, by our termination proof, the other argument decreases by at least 1 on each iteration. Therefore, if both arguments start with the same value, then the fuel can never run out too soon. And of course, since the helper function avoids fancy recursion, reduction should be fast and unproblematic. The big change in Lean 4.27 is that the elaborator now automatically performs this workaround when possible. You might call it auto-fuelification. When the elaborator sees a function that is recursive over a well-founded relation, it now checks whether that relation is the less than relation on natural numbers. If so, then it uses a new specialized fixed-point operator named nat.fix. Whereas well-founded .fix needs to work on any input type alpha, nat.fix knows that it is working on natural numbers, and therefore it can exploit simple structural recursion. A downside of this change is that it increases the complexity of the elaborator. Now there's a bit more distance between the source code we write and the kernel code that gets checked, but I think that's an acceptable price to pay. We can now efficiently reduce makeFiniteList 1024 with no problems. Everything we've been complaining about has been fixed. And that brings us back to the pop quiz. As of today, in Lean 4.28, reducing makeInfiniteList 5 returns a value. Since we didn't add a semi-reducible attribute, you might guess that the reduction immediately gets stuck. However, the reduce command is a special case that sees through irreducibility. What it actually returns is a list where the first element is 5, the second element is 5, and then after 6 of these 5s, the remainder is a weird stuck term involving false.rec. Can you see what's happening here? The reduction continues exactly until it runs out of fuel. And I think that's a fascinating, unexpected way that we can observe the implementation details of recursion.